I am going to talk about an exercise that must be carried out in order to develop the analysis and understanding of the watersheds, which is basically how to make a connection of the ecosystem services with the interventions planned in the basin within the framework of the water funds. So, in order to carry out this analysis of how interventions can be connected with ecosystem services, and finally how they can be included in terms of an economic valuation, the first thing is that an analytical framework must be taken as reference. This analytical framework corresponds to a series of steps to make the link between interventions, ecosystem services, and economic valuation. Interventions that can have an effect on ecosystem services must be identified, and for this, it is necessary to understand what the ecosystem structure is like, what the ecosystem function is like, what ecosystem services are like, and then move on to an economic sphere with the quantification of benefits and values. When the values are combined with the intervention costs, it is possible to do a return on investment analysis and ROI analysis. For this scheme, it is necessary to be very clear about the interventions, the ecosystem structure, and the ecosystem services. Very quickly, let's go back to the basic concepts. Interventions are any action to mitigate or address a water security problem. The ecosystem structure refers to the way the elements of an ecosystem are added to the landscape, its spatial and temporal configuration. And this is usually a technical exercise that takes time and requires a large level of knowledge of the basin. Understanding the ecosystem structure is fundamental to any modeling or analysis exercise. When we talk about the ecosystem function, we are talking about the processes that the ecosystem structure develops and performs. For example, the reduction of erosion. There is a direct link between the state of the ecosystem structure and the ecosystem function. This is really very important to understand when doing water system analysis. When we talk about ecosystem services, we are referring to the products or aspects of nature that support human uses. In this example, it is expected that an ecosystem function of erosion reduction translates into a service that can be reduction of the concentration of total suspended solids in municipal drinking water. This is just a particular example. Only when you have this understanding through the analytical framework, it is possible to assess the benefits. For example, in this case, the benefit could be associated with the reduction of treatment needs. Finally, it is possible to analyze the value it generates or the change in human well-being that generates the ecosystem benefits. For example, in this case, we could talk about lower cost of drinking water treatment. As you can see, this is a general analytical framework that guarantees the connection from the interventions to the assessment of benefits. To summarize, on one side, we have ecosystem services as benefits that nature provides to society, classified as provisioning services, regulation services, cultural services, and support services. On the other hand, the objective is to be able to build a link between ecosystem services with interventions. That fundamentally is any action that a water fund takes to help mitigate or address a water security problem. Traditionally, water funds carry out activities associated with the protection and conservation of ecosystems, restoration, repair and restoration, best agricultural practices, best livestock practices, or restoration of wetlands. During this process, there are a series of key questions that we must resolve. The first question is, what improvements in ecosystem function could improve identified ecosystem services? And the second question is what conservation activities can improve the ecosystem function? All the effort we are making is focused on solving these two questions. The questions are not so easy to solve, since to give an answer it is usually necessary to carry out a mathematical modeling exercise with an acceptable reliability to have a useful answer for decision making. To answer the first question, we need to consider that ecosystem functions are associated with processes carried out by the ecosystem structure. These functions may be associated with soil retention or aquifer recharge, among others. In this part, the ecosystem functions in which an impact can be expected with the interventions must be identified. Similarly, there are conservation activities. In this case, we must conceptualize, according to the understanding of the ecosystem, which actions can have an effect in the basin to be closer to the objectives that we have. Let's look very quickly at an example of identifying ecosystem functions and interventions in the specific case for drinking water treatment. In this case, the selected ecosystem service is clean water for the municipal drinking water supply. It is necessary to define a measurement unit, and in this example, the measurement unit will be the concentration of total suspended solids. This is the unit of measure with which we want to evaluate that we are going to have clean water for the municipal drinking water supply. At a conceptual level, it is possible to consider that in order to reduce the concentration of total suspended solids at the water intake, we must consider the ecosystem functions that, if improved, will reduce the amount of sediment that reaches the plant. And this intuitively identifies that one of the ecosystem functions of interest is soil retention. If we improve soil retention in terms of sediment retention, the expected effect is to have a lower concentration of sediments in the water intake for the treatment plant. Again, at the conceptual level, once the ecosystem function, soil retention, has been identified, determine which conservation interventions are likely to generate the greatest improvement in the performance of the ecosystem function. At this point, it is possible to identify what activities such as reforestation, repair and restoration, or forest conservation are likely to improve this function, understanding that with these activities, the properties of the soil change and the characteristics of soil erodibility improve, and therefore the ecosystem function also improves. These interventions must be listed together with their unit cost to perform the return on investment analysis. There are two components to consider when determining if an intervention is cost effective: spatial and temporal components. This is really interesting because it implies technical challenges to define where and in what timeline these interventions work. The fact of requiring an adequate spatial and temporal representation is fundamental for the analysis and adds a significant level of complexity. In this section, we will briefly see what this complexity means. To begin, I will refer to the River Styles technical framework developed by Professors Gary Brewley and Kirsty Fierce. In this framework, it is indicated that to understand a water system, three things are fundamentally needed. You need to be able to describe it, you need to be able to explain it, and you need to be able to predict it. In the description, you need to answer two questions. How does it look? And how does it behave? In the explanation, you must answer why does it look like this? What controls the behavior of the system? And finally, to be able to predict, you need to be able to answer what will the system look like in the future, and if X, Y, or Z is changed, how is the system more likely to respond? The answer of these questions is complicated by the fact that water systems are very special, mainly because they operate with multi-scalar relationships, from a watershed scale that influence a scale of reach, which is linked to a geomorphological unit scale, and finally with a microhabitat scale. When doing an analysis of water systems, one works with the relationships of multiple scales, and for this reason, the analysis can become very complex. The other thing that happens is that the water system do not respond immediately. They have a lag time. To make a link between the interventions and the effect on the ecosystem service, it is necessary to understand that to see the effect, we are going to have a lag time, which is the aggregation of time required for interventions to produce the desired effect, time required for the effect to be delivered to the water system, and time required for the water body to respond to the effect. All this complexity is reflected in the fact that we have two components for the analysis, a biophysical analysis component and an economic analysis component. In the biophysical component, mathematical modeling is one of the most important tools. So very quickly, let's talk about the most important elements of mathematical modeling. Models are simplified representations of reality. When a model is developed, we turn on or off certain relationships in order to have representations of reality, but always simplified. It is possible to have several models that represent different things with different levels of complexity, but always as a simplification of reality. So, why do mathematical modeling? And the reason is that if we return to the understanding structure of the water system, mathematical models help in the prediction component. They are tools that allow us to predict future conditions and know the response of the system if changes are made in mainly biophysical conditions. In a practical way, one of the interests in mathematical modeling is to be able to know the possible responses of the system with certain activities, change of land use, reforestation, best agricultural practices, green infrastructure, etc. So the main reason why it is of interest to do mathematical modeling is because we want to be able to predict the response of the system and to be able to build a link between activities and the response of ecosystem services. However, there is a fundamental question, and it is how to develop a predictive mathematical model. For this, it is necessary to recognize the complexity involved in studying the water system and adopt a technical modeling framework. To ensure a proper process, it is best to follow a standard mathematical modeling protocol that includes defined modeling goals and objectives, preliminary investigation, formulate the mathematical model, select or develop the mathematical model, model construction, calibration, validation, scenario formulation and simulation, analysis of results, presentation of results, and post-audit. To conclude, I would like to highlight that within the whole process that we have seen in this presentation, it is important to recognize that a rigorous mathematical modeling exercise is required to have a predictive model that allows connecting the interventions in the water funds with the ecosystem services. Thank you very much for your attention.